talking about kinetics. Kinetics is the definition. If you look back in your notes, you would see that it's the rates of reaction and the mechanisms by which they occur. We're going to get to the mechanisms next period. But I want to finish up the rates of the reactions. Where are we in this? Well, there are 4 things that affect the reaction rate. One of them is the nature of the reactants. Okay, you already have all of this, and no one's writing this down. But it's been spread out over the last several days with a lot of demos, video clips, and a lab. So you kind of forgot where we are. Nature of the reactants means things like different allotropes react differently. Subdivisions, that means increasing the surface area, powdering it, or solution in water, dissolving it in water. All of those are just changing the reactants before you put them in the same pot. Second, the temperature. We just did a lab on this, heated something up, same exact reaction, went about twice as fast, 10 degrees higher. Catalyst, talked about that a lot, section you had to do on your own. Homogeneous versus heterogeneous, how they work, you had to read that section. Also, that's using the transition state theory and the progress of reaction graphs, how they actually work. Now, here's where we are. That took us about, maybe 3 or 4 days, 3 or 4 periods at least, to cover. We're going to spend the rest of the chapter talking about this last one, concentration of reactants. That's our new notes for today. Concentration of the reactants. Okay, because we're going to start to get into calculations with this. We need to get to numbers. We need to actually put a quantitative value to the reaction rate and not just be talking about how we can make it go a little faster or slower. We need to talk about its actual numerical rate. And so that requires, first of all, today, these 2 periods are going to be mostly about the theory behind it. And then we'll get to the actual calculations. We'll get to the actual calculations later, okay? We'll probably start tomorrow. All right. What do we know about, what do you think is going to happen? Obviously, if I increase the temperature, things go fast. If I give a catalyst, things are going to. If I increase the concentration, collision theory says greater chance of a collision, greater chance of an effective collision, right? So the rate's going to increase with the increase in concentration. The reactants, no one's surprised by that. But what you may be surprised by, or not even realize you're surprised by, is the obvious corollary to that, which you probably can't see right now until I do this little thing with you, okay? Let me show you. Let's take a look at what would happen to a reaction rate. There's going to be some examples. There are going to be some examples you're going to make some mistakes on during this example, I should say. There are going to be some mistakes you're going to make. All right? Do not make a box as these pop up for this example, but write this equation down. A plus B, you'll see it. My things are going to come up as a box, but it just could be a chart. You're going to be putting some things underneath each of these. So you don't have to have an actual box. I had to have the box in order for it to work on my PowerPoint the way I wanted it to come up. All right. So initial concentration. Let's just say initially I have 1 mole of A and 1 mole of B. 1 molar of A, by the way. If you notice, it's a capital M, and a capital M means molarity. So I'm talking about an actual concentration. So I have 1 molar A and 1 molar B. Now, again, don't need a box, just a chart as we go along. I'm going to see what happens over time. How much C, and here's your first mistake. How much C do I have before they actually react? In other words, I put A and B into the container before they actually hit. Okay, I'm about to pour them in, whether they're gases, liquids, or solids, whatever, probably usually gases. Before they actually get together, how much C do I have? I heard the 2 wrong answers I was expected to hear. I heard 2 and I heard 1, both of which are bad, one of which is even worse. All right? Yeah, it's yours. How much do I have? Let me say it again. Before A and B ever touch, how much C do I have? 0. Yeah, I've got none. I got none initially. Okay? I tried to make that clear in my first statements, but I knew you would misread that. And that's okay. I know what you're thinking. One of you at least is thinking about stoichiometry, and yeah, we're going to have a talk about that, looking at that in a little bit. But another person who said one of the other answers is really, really wrong. We'll talk about that in a second. All right. For example, let's go to the really, really wrong answer. The person who says 2 of C, Kaylin. That was Kaylin, for those of you, for posterity's sake. Yeah. Let me show you why that's wrong. Okay? Even if we assume what she's talking about is that completion. If I took 1 mole of this and 1 mole of that, she thinks I get 2 moles of C. And that's completely wrong. And here's why. Let me show you. Here's one carbon. Here's one oxygen. If I put them together, how many carbon monoxides do I make? 1. Yeah, it goes by the coefficients, right? 1 plus 1 does not always equal 2, at least not in chemistry. Do you see why it doesn't equal 2 in this case? 1 atom of this and 1 atom of that give me 1 molecule of that, okay? 1. 1 plus 1 is 1, because it's the coefficients. It has to do with the coefficients. But anyway, that's not what I'm talking about here. What I'm trying to talk about here first, today, is what's going to happen over time to the rate of the reaction. So let's say we wait some amount of time x. We'll call this time x. Not time x watch. They still make time x's?
Yeah.
Well, after a certain time x, let's say I have used up half of a mole, half of our concentration of the A and B. Again, think to yourself, how much C have I made during this process? No, I'm still going to get a wrong answer, but what? How much C did I get?
0.
No, it's not 0.
1.
It's not 1.
0.5.
It's not 0.25. Are there any other answers we can get out there? All right, it's 0.5. This is all common sense stoichiometry, what you've learned in Chem 1. And let me show you why that works again. It goes by the ratio. I used up half of a mole of A and half of a mole of B. All right, whatever the number is, one of these and one of these. I put them together, I get one of these. If I used up a half a mole of A and a half a mole of B, I'm going to get a half a mole of C. Just for the same reason as, and I still can't believe people are looking at me like, huh? Kate is looking at me like that. 1A, do you agree with this? 1A plus 1B gives me 1C. If I had 2 A's and 2 B's, would I not get 2 C's? So if I have a half of a mole of A's and a half of a mole of B's, would I not get a half of a mole of C's?
Why does it say 0 then?
It does not say 0 here.
No, the one above.
The one above, I said before. You weren't listening, Taylor.
I was listening.
No. I watched you. You weren't listening. I said before they ever touch. A and B, you remember me saying that? So how can I have any C if I added A and B to the container and they haven't touched yet? That's why that's 0 initially.
Well, then how can you have 0.5?
Well, at this point, I've used up 0.5 of A and 0.5 of B have been used up. I've created half of a mole.
So they touch.
So they've touched. They've touched. Okay.
That doesn't make sense.
It doesn't make, nothing makes sense. This is completely impossible to understand. This is beyond the capacity of your brain cells. I haven't even gotten to the hard parts yet. You guys have a lot of work to do. This is not the hard part. I know, and every year I get the same thing. It's amazing to me, but every year I get this. All right, but I haven't gotten to the hard part. Here comes the hard part. All right, if I used up half of this after time x, here's the mistake I expect you to make. After time 2x, it's all gone, right?
No.
But it won't be. And that's the weird part. See, this is the sad, sad state of affairs here in this class. Everything I've just said up to here should have been, oh yeah, absolutely, 100% right. And that's what you had trouble with. Okay, now this is the new thing. Why after time 2x? Why after time 2x do I not go to 0? If half of it was used up in time x, I wait another period of time x, assuming it's going at the same rate, but there's the problem. It's not going at the same rate. Now we get back to my initial problem. The rate increases with increasing concentration of the reactants. I said there's an obvious corollary to this that you may have missed. If the rate increases as I increase the concentration, what happens to the rate as I decrease the concentration? It decreases. So from here to here, it was happening at a certain average rate. From here to here, over the next period of time, say 10 seconds for here, 10 more seconds for here. What was its rate now? Slower, right? Because I don't have as many of these guys banging into each other. So after that amount, I've only used up half the amount. Now we got the 0.25. You guys were, I think, well, you're just thinking ahead of me. That was the problem. You're thinking ahead.
That's not the easy part.
Yeah, but this is the hard part. All right, one last chance, and I know you're going to blow it. One last chance. At this point, how much total C will there be in that container? Careful. How much total C? Total amount, 0.75. You say, well, it should be 0.25. Guys, I know what you're thinking. Those of you who are thinking 0.25, you're right. 0.25 more was used up, but you have to add it on to the fact you already had 0.5 used up. Now, can anybody see what's going to happen if I keep doing this? What's going to happen after time 4x and time 6x or 8x and so on?
It's gonna be like 0.1.
Yeah, it's never. Is it ever going to get to 0 if this is a math problem? No, it's just going to keep approaching 0. In fact, in reality, you will eventually get to 0, even though in a math class you never do. Because why will I get to 0? Because we're starting out with 1 mole of this stuff, right? That's 6.022 times 10 to the 23rd atoms. And 6.022 to 10 to the 23rd. That's a lot. But after time x, half of those atoms are gone, right? And after time 2x, whatever. We keep cutting them in half as we keep waiting more and more time. Eventually, what will I get down to having? Just 1 atom, right? Can I cut an atom in half? No. So once that last atom's used up, it really is at 0. Now that actually is called a reaction that goes to completion. That doesn't happen very often. Most reactions don't go to completion, but we talk as if they do a lot of times when we're doing, especially in Chem 1. All right, so let's write this down so you understand it. And this is all in words, what I just got done explaining, okay? The rate of the reaction decreases as the reactants are used up. So, because of that, the reaction rate is going to drop, right? The reaction rate is going to decrease. And it's not going to decrease linearly, is it? It's going to decrease in a nonlinear fashion. Something that you've probably graphed before, but I'm going to graph it with you again. And again, there'll be lots of opportunities for you to make more mistakes, so hold your horses. I'll have good chance for you. I'll be asking questions again, see if you can make mistakes again. And I know you won't disappoint. But you all probably see what's going on now, and I've explained it, I hope. If you can see past these chips. These are Lexi's chips. This is what you usually hear in the background. Just thought I'd tell you. And now you're immortalized too. You happy now? Kate, Kaylin, Lexi, and Taylor. All immortalized forever. Assuming I keep this one of the uploads. All right. Good enough? Everybody good with that? All right. Let's try graphing this. Let's try looking at a graph of this. In order to graph it, I have to have a way to measure the rate. We can measure the rate in 2 ways. We can measure how fast the reactants are used up or how fast the product is formed. And you saw we did this in the lab. Again, that was a very easy lab compared to what we're about to do. Well, we just calculated how long it took to produce a certain amount of gas, oxygen gas, from that reaction, remember? We collected 150 milliliters, saw how long it took, figured the average rate over that time. And of course, it increased when I heated it up. That's no real surprise to anybody. So we can measure the product. Oxygen was a product being formed. We measure that. I could also measure how fast something disappears. We can do that. There are labs where you do that to measure the rate. Sometimes you can use a colorimetric technique for example how fast the color is disappearing. Okay, using a spec 20 or spectrophotometer. We are going to use something like that in a lab also coming up. All right. Now let's get an example here again, a real life example, not just an A plus B example. Let's use real, and by the way, it's a very common equation to see used. N2O5 and use NO2 and O2 balance. I want to graph this. I want to see over time what's going to happen. Believe it or not, in this chapter, people, graphs are a big deal. Unfortunately, in a case, the graph I'm going to show you here, I think, is absolutely essential to understanding kinetics. And I've always shown it for 30 years of teaching. The other graphs, unfortunately, I kind of ignored over the years and have had to teach because of AP chemistry. All right? And I'll be showing you those tomorrow. All right, but this graph in particular is essential to understanding what's going on. So I want you to make this graph with me. In order to do that, I have colors. You don't have colors. We're going to make each of these guys a different symbol, a circle, a square, and a triangle. And we all have to be consistent on this. So make the N2O5, put it underneath him. You're going to make him a circle, a triangle for NO2 and a square for O2. I'll also use different colors so it'll be obvious to you guys. And we're going to make this graph. Make 2 lines. And by the way, look at your paper. Assume that's your paper here. This is how many lines of your paper you need in order to do this correctly. See? So you can put a 4, 3, 2, 1, 0. And then you can have concentration over here. Now, the only thing that's going to be different is you don't need to actually put down time 1, time 2, time 3, like that. All you got to do is just put time on the bottom, okay? We'll just put time on the bottom. I'm not worried about you getting it perfectly, you know. I had to do it this way again, so the graph would come up the way I wanted it to in my PowerPoint, or my Keynote, actually. I don't like PowerPoint. Sorry, Microsoft. Not getting my endorsement. You know, I got a lot of people on YouTube following this, and that's going to really come as a shock to Microsoft. I'm probably going to get sued now, but don't like PowerPoint. I'd rather Keynote. This is Keynote. Notice, are these better transitions, more fun ones? I like them. I even use a parchment, right? I feel like you're back in the Middle Ages. All right, questions. Time for some questions. Let me ask you something. Where would I, bless you, bless you. Where would I start? Again, initial. You got to think, before they've touched. Where am I going to put my circle, triangle, and square? Okay, well, first of all, let's go left to right. Which side are they going to be on, the left or the right? What do you think? Okay, everybody agrees it's to the left, to the left, to the left. Good. Oh, I didn't want you to see that. I touched it, sorry. Didn't mean to touch it. Meant to have this on. All right, so we have the circle and triangle and square. Where are they going to go? Initially, what do I have? How much of this do I have? Assuming I use stoichiometric amounts. I have 2, so I'll put my circle here. Oh, I want to use red. I want to use the same colors. Okay, that's not red, even though I hit red. I told you how much I love these PowerPoints. Keynotes. They're actually keynotes. Oh, please. All right. All right, let me ask you, where is the initial amount, where are my initial triangle and square going to be? They're going to be at 0, aren't they? Right? So I'm going to make my blue triangle and my black square at 0. You see why they have to start at 0. They haven't started reacting yet. And N2O5 hasn't started reacting yet. So he's still just N2O5, and there are none of this. Now, if the reaction goes to completion, which again, most reactions don't, and we'll learn about those when we get to equilibrium. But if the reaction goes to completion, how much of that N2O5 will there be at the end? Right here at the very end. Down to 0, right? Again, I hit red, and it's not going to do it for me, though. There's the red. Won't it end there, right? Let me ask you this now, a tougher question. Where's that blue triangle going to end up? Think about it. At 4, right? You see why? I think I have 4 times as much NO2 as I have, 2 to 4 to 1, okay? So you have 4 up here for the triangle. Where would the O be? The O2 be? And the black square would be at 1. Got it? Now, I didn't mean to hit that board so you all saw what's going to happen, but I was going to ask you, how are these going to change? Well, I think there's one thing we all are agreed on. It isn't going to change like this. It's not going to be a linear line, right? It's not going to be a straight line, okay? Why, as you already saw what happens, why does it end up looking like this? Why does it end up looking like this? And by the way, you want to make this in a nice smooth line. You want to draw this line, but make it smooth. Again, I had to use the program that does this, so it makes it choppy. You make a nice smooth line, okay? Why does the graph look like that? That's my question to you. Because what?
It halves every time.
Well, yeah, but I mean, in terms of, now I'm asking you in terms of explaining in terms of the reaction, what's going on. It drops really fast in the beginning, and then it doesn't drop as fast. Why? What's happening? The concentrations are decreasing, and therefore, the reaction is slowing down. The rate is slowing down. So the rate between here and here is faster than the rate between here and here, and is faster than the rate between there and there and there, right? Make sense? The rate's slowing down. Why is it slowing down? Fewer and fewer N2O5s are left to bang into each other or do whatever it is that they do. Fewer and fewer of them are there, right? Okay. Now, can you tell me, now that you know that, can you tell me what the shape of the blue and the black graphs would look like? You know it's not a straight line up to there, but what would it look like? Can you figure it out? Would it be, would it look like this, or would it look like this? What do you think? Yeah, because again, we want the fast reaction to be happening early. It's happening a lot. You're getting a lot of it early, and then less and less and less later on. So that's why that graph looks like that, and that graph looks like that. And again, you want to make a nice smooth curve, even though I had to do it like that. This graph is essential to understanding what's going on in any given reaction. The other graphs I'm going to show you are going to be for basically predicting the order of the reactions, which I'm going to try to explain to you in the next period, next half of this class. But you have to understand what's going on here first. Okay, if you don't, you're going to be in trouble because the rate is constantly changing. Hey, that brings me down to something. When I say the rate's changing, I can measure that rate. The rate is the concentration change over time. If you were in geometry class, what would you call that? The change in concentration over the change in time would be called the slope. It's the change in y over the change in x, isn't it? Isn't it? Isn't it?
Yes.
Yes. Okay. Now here, listen to this. That would be geometry class. What class would you be in realizing that these are not straight lines? You know, in geometry class, your lines look like this almost all the time when you calculated your slopes. What do they look like? What class, if I'm doing this? Yeah. Notice that slope, the tangent to that curve is constantly changing. The definition of calculus is the mathematics of when two things are changing. I mean, basically, that's the definition of calculus. You have a change in y over the change in x. You have a change because you're talking about the change in the rate over time, the change in time. How many of you guys are in calculus? Okay, that's almost all of you, and that's a good thing. Now, the good news is, don't worry, we're not doing calculus here. We're not going to be doing derivatives. We're not going to be doing integrals. We're not doing that. All right? However, don't worry, we're not. However, do you see why that would obviously classify as calculus? You're changing the concentration's rate as well as time at the same time. Your instantaneous rates are always different along this. And all we can really do in our labs usually is get an average of that rate between a certain small part. If I take a really short distance between two, that would be really close to the derivative, right? Very close. Okay? All right. But don't worry if you don't have calculus, it's not going to kill you. So everybody good with that. Now you notice the slopes. I got to have a way to calculate. I said the way to calculate the rate is by calculating the slope. All right. However, do you notice you're going to get three different slopes here, aren't you? All right. We got to worry about that too. And now I'm going to talk about that in a second. At any given time, the slopes are changing. Okay. They're related to each other in a way, but I want to tell you how that's related in a second. Let's do this. Okay. So the rate of the reaction, as I just said, is the slope of the tangent to the curve of the products at a given point. That's what the rate's going to be. Does that make sense? That's a fancy, fancy way to say that you're simply measuring the change in concentration over time. The moles per liter per second. Okay, how many moles per liter per second you're using up? How many moles per liter you're using up per second, I should say. So I could actually write that as an equation. If I'm talking about the products, the equation would look like this, wouldn't it? The rate would equal change in y over change in x, which is a change in the concentration of the products over the change in time. Is that right? Make sense? Everybody should get that. Shouldn't be a real surprise after all that explanation. However, after you copy that, we got another problem. If I'm using the products, I don't have a problem. But let's go back at that graph. I'm going to come back to this. Don't worry, I'm not going away. I'm going backwards here. If I'm using a product, I have no problem. I'm definitely going to get a slope that is also the rate of that product. What's the problem with using the reactants? Yeah, the slope's going to be negative. Notice that the change in y is a negative value, isn't it? It's going down. Whereas the change in this way, both of them are positive values, so your slope's positive. Here, you have a negative slope, don't you? If I put a tangent to this curve, I would be a negative slope. Okay? All right, so what do you think I'm going to do to change this equation? If I'm going to do the rate, it's going to be the negative change in y over x. If I use the reactants, that's what I have to do. I have to take the negative of that value. All right, that look good to you? Everybody okay with that? I hope you all understand that graph. And I'm not quite done with it because there's one other thing we have to worry about before I leave you go, and have some basic questions on it. We'll do some examples as well. 7 to 10 of your homework is on this. All right. I took care of, first of all, everyone understands why it's the slope. Secondly, everyone understands why it's the negative slope for the reactants and the positive slope for the products. Now, we also have coefficients. We have to worry about them too. Let me show you how that works. And this is the reason I'm taping it today, because what's up there right now, Michelle's probably watching. Hi, Michelle, if you do end up watching this. Michelle's going to be gone for weeks. So while she's watching this, okay, so Aaron just realized that. Anyway, while she's watching this, if she watched the previous one, she would not have seen my explanation like this. I think this is a better way to explain it. Because when I was explaining it yesterday, I realized, as I was looking at the faces of people, kind of like your faces the first 5 minutes of the class, it wasn't getting through. So I decided to make an analogy. And it's a really good analogy. You're going to like it. It has to do with food.
Nice.
Food. Food, Lexi. You hungry? Huh? Yeah. Food. Sandwich. I heard that.
So did the video.
So did the video. All right. I'm going to make a sandwich. To make the sandwich, I need 2 slices of, you don't have to, obviously not, put down your pencil, Lexi. Stop copying bread. She's writing bread down. I need 2 slices of bread, right? And let's just say I'm making a sandwich that somebody of you would like. I don't know. I want a slice of cheese, 1. I want 2 tomatoes, and I want 3 pickles. It's a pretty ugly sandwich. I would not eat this sandwich, but just say. Those are the graphics I can find online. So that's the best I can do. They do look like cucumbers. But do you know cucumbers are actually pickles? Did you know that? They're pickled cucumbers. That's what they are.
That's what people say.
That's what pickles are. That's what cucumbers are after they're pickles. Anyway. Look. Now, the reason I'm using this analogy is I want you to realize something. Okay, you watching? Okay, look at it. So basically, here it is in numbers. I need 2 pieces of bread, 1 cheese, 2 tomatoes, 3 pickles to make 1 sandwich. My rates will be different. Say, for example, I'm working at a deli, and I'm making sandwiches at a rate of 5 sandwiches per minute. I don't know if you can make 5 sandwiches in a minute. I doubt it. But let's say I'm making a rate of 5 sandwiches per minute. Okay? I might also have a rate of 5 pickles per minute. How many pickles am I using per minute? 15. How many tomatoes am I using per minute? 10. So their rates are all different. Per minute, I'm getting 1 sandwich, but I'm using 15 pickles, 10 tomatoes, 5 pieces of cheese, and 10 bread slices. So all of those rates are actually different. All right? The change in the number of sandwiches over time does not equal the change in the number of pickles over time. It would equal 1/3 the change in the number of pickles over time, wouldn't it? In order for this number to be exactly the same. Would you all agree with that? Right? You all make sense? It'd be 1/2 for that guy. Would it be the same as the rate of the cheese disappearing? Right? Right? That would be the same. Oh, what would be different about the rate of the cheese disappearing? What would have to be in front of both of these numbers? A negative. Oops. A negative. And a negative. And a negative in front of that one too. Because these guys are all disappearing, where mine I'm getting more sandwiches. Okay. Now, having said that, can you answer a question kind of like this? Copy this question down. It's my example. if I wanted to be able to express the rate of the reaction, okay, so that would have the same number no matter what reactant I was using, what would I have to do? Copy that guy down. These are the kind of questions you're going to be getting on the homework tonight, okay? And again, notice I use the same equation I used before. It's a very popular equation to see. I've noticed it show up in a lot of AP questions, all right? And so I try to pick things out that I hope you'll see again. You don't even realize it most of the time, but my examples are, I have found that the examples I've chosen, kids will come back and they'll be the exact same examples they'll have on tests, problem solved on tests in college, okay? Because there are certain ones that are just used more often than others. All right, so here's my question to you. Okay, for oxygen, what would the rate of the reaction be? Well, the coefficient of oxygen is a 1, so it's relatively simple. The rate's just going to be the change in the concentration of oxygen over a change of time. Now, given that, using that as the rate, what would the rate of the reaction using NO2 be? Okay, notice NO2 is really, you're getting 4 times as much of him. So if you wanted to get the same number as you got over here, wouldn't you have to take 1/4 of that number, right? Does that make sense? And what would you need for the N2O5? Yeah. That makes sense? Notice something else. What else did I need in front of that N2O5? A negative. Because he's disappearing, he's not appearing. Okay. Everybody good with that? That's one kind of question you can get. That's the kind of question I think is in like number 7 and 8. Then you got like 9 and 10, which are going to ask you a question like this. And this is where I really changed things up when I was teaching this class to the other. Not only did I add the sandwich and pickles thing, but I also changed this problem completely because it's a different kind of question it's asking. Read that question. See if before I show you how I want you to do it, I want to base. And by the way, you've already written this equation once. If you don't want to have to write it again, you've actually written it like 2 times. If you don't want to write it again, it's okay if you leave it out. I have it up there so we can see it. But it's the same equation I've been talking about. N2O5 yielding NO2 and O2. So you want to save yourself a little bit of writing, you can just leave it out for right now. But look at what this question is saying. And notice how even weirdly it's worded. Specifically it's worded. Okay? It has to be worded that way to ask the question it's asking. Here's what it's saying. It wants to know the rate of production of NO2 at the same instant N2O5 is being made at 3 molar per second. N2O5 is being, N2O5 should be is being used up. It shouldn't be made. It's not being made, right? Used up. Sorry. I just changed this one, so I will have some silly mistakes like that. N2O5 is not being made. He's being used up. So at 3.0 molar per second is disappearing. What must the rate of production of the NO2 be? Okay. Now here's how I decided the best way to teach this one, once you get that all copied. Stoichiometry. If this were a stoichiometry problem or any other stoichiometry problem in the world, you know what stoichiometry problems were. We did them with the alcohol lab most recently, but of course in Chem 1 we did a bunch of them. The alcohol lab, you started out with 30 grams of sugar, right? 30 grams of C6H12, actually it was C12H22O11. And you wanted to go through a whole bunch of conversions until you got to how much C2H5OH, how much alcohol we got, right? That was our whole lab. So your first step, guys, when doing these problems, doing any stoichiometry problem, what's your first step? What do you write down? The given. You write down the given information. So let's write the given information. We have 3 mole. We know we have a rate of 3.0 molar per second being used up of the N2O5. I know that. You know what to do. You know exactly what to do. Oops. You're going to put units on the bottom of what you have and units on the top of what you're looking for. We have moles of N2O5. We're looking for how many moles of NO2. We want to substitute those in there. And you fill in, where do these 4 and 2 come from? What do you fill them in with? The coefficients. Exactly like you would have done a stoichiometry problem in the past, and you get 6. That's why you get 6 mathematically. But doesn't it make sense? Now, forget about the math, guys. Forget about the math. Let's just lose common sense. If I were to give you this problem and you weren't thinking about all the other crap, you were just looking at the problem. If you know the rate of N2O5 disappearing is this, 3 molar per second, and that guy is going to be making it at twice the rate, right? 4:2, twice as big. Wouldn't you have predicted it would have been 6? I think you would have, right? You would have predicted the rate of sandwiches, pickles. That's what I'm talking about, like that. It would have been 4 times. This guy's 2 times, so it's twice as big. That's twice as large. All right, one last one for you to do on your own. If you get this right, same again. You don't have to copy the equation down. If you get this one right, you know what I'm talking about. It's not hard. Same basic problem. Oh, and in case Maggie's watching this at home too, hoping Maggie feels better. She also had her wisdom teeth out along with pretty much half my class over the last month. Feel better, Maggie? Anybody know if she's doing any well? Any better? She's chubby? Okay. Chubby Maggie. It's because of the wisdom teeth. And all that ice cream. You don't eat ice cream after wisdom teeth. You shouldn't, right? You should know, dry socket girl.
I did.
Oh, and
I did.
sorry, Carly, we got your video. I should post that one online. She's crying.
I had no idea what was going
She didn't know. She didn't remember it anyway. If somebody didn't tape it, it wouldn't even know. All right, did you all do this? Take your initial, or your given, I should say. What do you mean? Come on. Hurry up. What are you guys doing? Yeah, listen to me. Nobody listens to me. By the way, you see Carly's pictures on all the posters around? The posters on the hallways? It looks just like her.
That's what my mom said.
Exactly. You know what I'm talking about. The one where she's sticking her tongue out and smiling at the camera?
Yeah.
Yeah.
My mom said the same thing.
It's exactly like her.
Where?
I'll show you. We'll go steal one.
Okay.
No, I will. Hey, what did you do here? Did you do this right? Oh, and by the way, this should be molar, not moles. This should be molar. You should have had molar per second, right? I don't know why I put moles there. It's molar per second. Again, I got little things. I just made this up. It would be. Would your conversion look like that? Is that what it looked like? Right? Is that how you had it set up? Kate? Why not? Look, you're given on the bottom what you're looking for on the top, and what goes next to the coefficients. 4 goes next to him. 1 goes next to him. Right? What?
I did it.
Okay, then what are you erasing?
Oh, I just.
Didn't do it. I did it, but I didn't do it. All right, so what's the answer to that guy anyway? What'd you guys get? What'd you get, Mag? Not you, Maggie. What'd you get, Maggie?
0.001.
She got 0.0018. Okay. I don't care. Whatever. Close enough. All right, I gotta go steal.
Moles per second.
That's yeah. The rates are still molar, not moles, molar per second. Because you're saying to yourself, well, how can it be? Because this moles cancel with the moles of NO2, but it replaced it with those moles, and it's still molar per second, moles per liter per second. All right, now the homework is page 652, numbers 7 to 10. For those of you who aren't with us, those of you who have passed on. All All right, I better shut this off before I can't use it anymore.